Welcome everyone. In this video, we'll take a look at the second section in Chapter 9 here, discussing series and convergence. We're not skipping past the first section. We covered 9.1 right before spring break. It's okay if you don't remember all of that information. If you want to take a look back in your notes, you're more than welcome. Most of the information that we take away from Chapter 9 takes place after 9.1. It's just a nice little introduction section. So what I'll do today in this video here is introduce what we call infinite series and talk about their convergence and kind of where we're going with this information. Okay, so let's say I have a sequence. If the sequence A1, A2, A3 to AN and then beyond is called an infinite sequence, then if I sum those numbers up, if I take each of these terms, A1 plus A2 plus forever and ever and ever, I get what we call a sum or an infinite series. This is called an infinite series. And we arrive at it from adding up terms in a sequence. Okay? So they're two slightly different things. The series is actually adding those terms up. Now, the numbers, AN, A1, A2, A3, so on and so forth, are called the terms of the series. Okay? Terms of the sequence, terms of the series. We use the word term in both contexts. I will very frequently talk about the first term of the series, the second term, or the terms of the series. Okay? So what we'll be looking for is whether these series, if I'm adding these numbers up, do they converge? What does that mean? Do they approach a number? If so, can I determine maybe what that number is or what actually is the sum of the series? What happens when I add all these things up? So that's what we're going to be looking for. In fact, three things that I care about dealing with infinite series. The first is whether or not these series converge. Does the infinite sum converge? Actually go to somewhere? Does it add up to a number, right? If I take a bunch of terms, do these approach infinity, a number? What? Number two is, what is that number, right? Or what is the actual sum? So not necessarily what they converge to, but what is the sum? When I add these up, do I get, say, negative 12? I don't know. Just for example. Do I actually come to a value, or does it go off to infinity? So those number one and number two, they feel kind of like the same thing, but there's a subtle difference. Determining if the series converges is mainly what this chapter is about. Because in general, we're not going to be able to determine actually, hey, if I add all these things up, this is what the answer is. Like, this is what the numbers add up to. We'll just be able to say, oh yeah, in the future, way far out, these actually add up to a number. Basically, what we'll be looking for is that they don't kind of explode, that they don't keep adding and adding and adding and go off to infinity. Okay. The third is kind of what we're gearing all of this towards, is to write functions as infinite series. Okay, and that's a little bit abstract, but say maybe we'll be able to write sine of x as this infinite sum. We'll get to that later. Like I said, basically what we'll be looking for is determining convergence of all these. Does this series actually an okay thing to write down? Does it approach a number? And then eventually, hey, let's try to write this function as a series. There are times where that's a beneficial thing, and that's what we're getting to. But first, what we want to try to figure out is, does a series actually converge? Okay, and if so, what is the sum? So first, to find the sum of the series, what we do is we consider what's called the sequence of partial sums. Sequence of partial sums. Okay. So what we'll look at here is basically, say I have a sum of a sub n what I want to do is I want to try to start adding up the numbers in that series. The first one is A1, right? And I'm just going to add that to itself. Basically what I'm doing is I'm going to go out one term in my series. One term. I'm going to take the sum from 1 to 1, a base of n. That's just going to give me a sub 1. And I'm going to keep doing that. I'm going to keep stepping one term further in my series and looking at the sequence of those things. Okay, not just the a's, but what happens when I start adding things up. Am I going to approach a value or not? No, I'm sorry. I sped up a little bit. So here we have then S2. S2 is going to be the first two terms in my series, which is A1 and A2 added together. S3 is the first three terms added together, so on and so forth. Okay, and what we get from this is a general nth term. We get some sequence that's given to us by taking the first kind of n terms, general number of terms, and adding them together, A1 plus A2 all the way to AN. If this sequence of partial sums converges, okay, if that sequence approaches a number, then we can say that the sum approaches a number. Then the series is said to converge. Okay, so this is really the definition of convergence here. If I have a series and I look at its sequence of partial sums, if I look at the sequence generated by taking the first term, adding it to itself, right? Or I'm sorry, just leaving it by itself. The first two terms, adding them together, the first three terms, adding them together, those make up the terms in my sequence of partial sums. If that sequence converges by taking a limit as n goes to infinity, then I can say that the series converges, and I do indeed then know what that sum is. That'll be S. Okay? Now, this is the kind of the long way to do things. In fact, for most of the chapter, we'll be looking at kind of shortcuts to determining if a specific type of series converges or not. Okay? So, for example, let's look at the first 5 terms of the sequence of partial sums. So really I want to determine if I can figure out the sum of this series, whether it converges or not, and then to maybe what number. Okay? So the first 5 terms, not of the series, the first 5 terms of the series are these here. When I take 1 over 2 to the n and I let n be 1, I literally plug in 1 for n. That's 1 over 2 to the first. And then I add to it 1 over 2 when n is 2, 1 over 2 squared, 1 over 2 cubed, so on and so forth. So I've written the first 3 terms there. I can keep going, of course. The sequence of partial sums is by taking the first term by itself. S1 is just the first term. S2 is generated by the sum of the first 2 terms, right? So S2 is 1/2 plus 1/4, which is actually 3/4. Okay? S3 is generated by taking the first 3 terms and adding them together. So what I see from that is I can actually use 3/4 because that's the first 2 terms added together, and then I'm adding 1/8 to that to get 7/8. The fourth term in my sequence of partial sums, S4, is taking 7/8 and adding 1/16. I get 15/16. If I go out one more, I should get 31/32. Okay? And basically what we want to try to figure out is, does this sequence converge? Where does it look like those numbers are going to? So I look at the sequence of partial sums, S1 all the way through Sn, and so on. Sequence of partial sums, those guys there that I have written in my various colors. I find the nth term. The nth term. I want to try to find a pattern for how this is going. Well, what you try to look at here is the subscript, right? Which term is this? This is the 5th term, say, and I have 31 over 32. Well, the denominator is 2 to the 5th, or 2 to the n. The specific n I'm working with is right there in the denominator as an exponent. So what I can do is I can generalize these terms by saying the numerator is 1 less. The nth term is, the numerator is 1 less, so it's 2 to the n minus 1 over 2 to the n. Okay? And does this converge? Does the sequence converge or diverge? Does that approach a number? Let's take a limit as n goes to infinity of this sequence. And I can try to manipulate things. We could use L'Hopital's here, but indeed there's one term on the bottom that I can split things apart, right? I can take 2 to the n divided by itself, and I get 1, minus 1 over 2 to the n. And as n goes to infinity, 1 is going to 1, and 1 over 2 to the n is going to 0. So 1 minus 0, this the sequence of partial sums converges to 1. So therefore, by what the definition said on the previous slide, is that the sum of the series here, 1 over 2n, is actually 1. The sequence converges, the sequence of partial sums converges, and that tells us that the series also converges. Okay? Hopefully, we don't have to go through this process every time. Okay, there's some shortcuts that we run into, or generalizations based on the type of series kind of that we're given or that we're looking at. In fact, the series here, 1 over 2 to the n, the series in the previous slide, or previous example, is called a geometric series. Okay, and all geometric series have this specific shape. The sum from n equals 0 to infinity of a times r to the n. If I write these terms down, I see a plus a times r to the first, plus a times r squared, plus a times r cubed, so on and so forth. And I notice that when I go from one term to the next here, there's a common ratio of r. All right? R is being multiplied each time. I'm adding a power of r. We say r is called the common ratio. Okay? And basically what we'll be able to determine is that a geometric series converges, approaches a number, I'm not going to prove this, but when the common ratio is less than 1. And basically the reason that makes some sense is that as I continue further out in my series, I'm raising this common ratio to higher and higher powers. And if that common ratio is less than 1, and I keep raising it to higher and higher powers, it's eventually going to go to 0, right? So after so long, it's basically like I'm adding nothing to the end of my series, okay? Or in other words, when the common ratio is between -1 and 1, okay? But it has to be less than 1 in absolute value. And the series diverges, or does not approach a value, or does not add up to a finite number, okay, when the common ratio is larger than or equal to 1. If I take 1 and add it up forever and ever and ever, right, if I just take the sum of 1 to the n, or just 1, forever, I'm just going to keep adding 1. This is going to diverge. It's going to go off to infinity, right? But maybe if I'm adding numbers that are getting smaller and smaller, in the previous example, I kept adding powers of a half, right? If I keep adding powers of a half, I'll eventually go to 0, right? Not that the terms add up to 0. We saw the sum from the last example was 1. But the terms, as they continue, will eventually approach 0, okay? So I want to look at a couple other examples here, and I want to write a formula down for you. We can find the sum of a convergent geometric series, and it goes like this. Of course, when r is less than 1, it has to be convergent. If I have the sum, let's say we'll start at k, when n is k, from k to infinity of a times r to the n. As long as r is less than 1, this series will converge to. It will actually add up to this number, a times r to the k, divided by 1 minus r. Okay? where AR to the K is what we call the first term of the series. In other words, the first term divided by 1 minus R. Okay. Again, I'm not going to show you exactly where this comes from. It's in the book. They go through the derivation of this formula. But basically what I want you to take away from this is that I can find the sum of the convergent geometric series as long as R is less than 1 in absolute value. Okay. So again, convergent and finding the sum here are two different things. It seems like the same thing. And that's just because we're working in a geometric series case, okay? But in general, just because a series converges doesn't mean that I know what it converges to. For example, let's take the previous 1 over 2 to the n and just kind of, instead of looking at the sequence of partial sums, go a little quicker and use our formula here, okay? So as long as R is less than 1, let me rewrite this a little bit. That's the sum from 1 to infinity. 1 over 2 to the n is the same as 1/2 to the n, right? Where R, my common ratio, is 1/2, and that's, of course, less than 1. So this series, converges to, the sum is equal to the first term, 1/2, to the power 1 is the first term, divided by 1 minus the common ratio. So what I get is 1/2, divided by 1/2 is 1. The sum is actually equal to 1. And that mirrors what we saw on the previous slide. So we used the definition before. We looked at the sequence of partial sums, and we were able to show that those eventually went to 1. With our kind of shortcut here, our shorthand formula for geometric series, we can find the sum using the first term divided by 1 minus the common ratio. Let's look at two other examples here. First, I want to find the sum, if it exists, or determine whether the series converges or not, of number 1 and number 2, these two different series. The first one here, I'm just going to kind of write out a few terms. I notice that n is starting at 3, which is a little different, but what happens here is the numerator is 5, and I'm dividing by 2 to the n. So did this converge, and what's the sum? 5 divided by 2 to the third is the first term, plus 5 divided by 2 to the fourth, 5 over 2 to the fifth, so on and so forth. My common ratio here does not include the 5. It's still just 1/2. Right? Because when I go from one term to the next, the power is only increasing in the denominator. The common ratio is still just 1/2 here. So that's what I want to show you. Just because I've changed this a little bit and added a 5 in the numerator doesn't mean my common ratio has changed. So when I go from one term to the next, there's still there's a factor of 1/2 that's increasing. Since this common ratio is less than 2, this series converges to the first term. That first term is 5 over 2 to the third divided by 1 minus the common ratio. 1 minus 1/2. Okay. And then I simplify. That's 5 over 8 times, in the denominator I'll have 1/2. So that's times 2 over 1, or 5/4. Okay? This series actually adds up to 5/4. Okay? Well, that's kind of a nifty thing. It converges because the common ratio is less than 1, and I can find the sum by the first term divided by 1 minus the common ratio. The second example here, I have 9 times 7/4 to the power n. There I'm taking all 7/4 and raising it to the n. So I want you to notice the difference between these two guys here. And we notice that when I go out some terms here, I have 9 times 7/4. N starts at 2, so that's 7/4 squared plus 9 times 7/4 cubed plus R is 7/4. Right? I'm increasing the power of 7/4 by 1 each term. for each term in my series here, that common ratio is larger than 1. This series does not converge. This series we say diverges, and we say it diverges to infinity. If I were to keep adding these terms up, they would go off to infinity. Okay? So that's basically what I want to look at geometric series-wise. We're looking for a times r to the n in the general, in the summation notation there as our nth term, and we're able to determine quickly if it converges or diverges. Let's look at another example. Find the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Okay. This does not quite look geometric, but let's go out some terms and see if it is or not. So what I do is I let n be 1, and I look at the first term. 1 over 1 minus 1 over 1 plus 1 is 1/2. Okay, that's the first term. That's like a1. When I add to that, a2 is when n is 2. So that's 1/2 minus a third. When n is 3, 1/3 minus a fourth, so on and so forth. Because I don't really see a geometric series here, I don't see a power increasing every kind of time. I don't see a common ratio. I look back to the sequence of partial sums. That's really all I can do, at least for right now. The sequence of partial sums is the first term, right? 1 minus 1/2. When I take the second term of the sequence of partial sums, that's coming up with those first two terms added together, right? Not just 1 and 1/2, but 1 minus 1/2 plus the whole next term, that a2, 1/2 minus a third. And you notice 1 minus 1/2 plus 1/2 minus a third is just 1 minus a third. Those 1/2s are going to cancel. I do this again. S3 is the first three terms. 1/2 minus a half cancels. 1/3 minus a third cancels. And I have 1 minus a fourth. If I keep going, eventually I'll get to a place where kind of all the terms, except for the first term and kind of the last term where I've ended up, if n is n, then everything up to 1 over n, or 1 over n plus 1, will have canceled. And I have 1 minus 1 over n plus 1. And again, that comes from 1 minus 1/2 plus 1/2 minus a third plus a third, so on and so forth, plus 1 over n minus 1 minus 1 over n plus 1 over n plus 1 over n plus 1. Everything in here cancels, and I'm just left with this 1 over n, 1 minus 1 over n plus 1. Sorry, tongue-tied. Okay, that's my sequence of partial sums. So my sum here, 1 over n minus 1 over n plus 1, should be the limit of this sequence of partial sums, the limit of Sn, and for us, that's the limit of 1 minus 1 over n plus 1. As n goes to infinity, by definition, the sequence of partial sums, if it converges, then the series converges. This goes to 1 minus 0, or 1. So the sum, the series, converges. And this is actually what we call a telescoping series. And that's because I see this cancellation effect everywhere I go. All right, so what we like to do is to generalize what we call this telescoping series. It's telescoping because it like closes in on itself, right? If you crunch in a telescope, that's kind of what's happening here. It closes in on itself, and we try to generalize this by not using A1, A2, A3, but each kind of individual term within a term, if that makes sense. B1, B2, so on and so forth. Every B is going to cancel except for the first and last. And a telescoping series converges if Bn converges. Okay? And in this case here, sorry, let me go back and just erase down here a little bit. Where's my eraser? Bn, if Bn converges, then the series converges. So what we do is we look at the limit of Bn, and if we get a value from that, then B1 minus that value is going to be the sum of our convergent series. Actual sum of the telescoping series. Okay. I'm going to do another example of these. And in fact, kind of thinking about it as a telescoping series, going into the next example here. But we basically try to find this sequence of partial sums shortcut. We try to find this Sn, and then we take a limit. So what we have here, find the sum of the convergent, or if of the sum of the series if it converges. Okay. So I have here the sum from 1 to infinity of natural log of n divided by n plus 1. Right? So I'm already kind of thinking telescoping. As it sits, however, this doesn't really look too telescoping. Right? If I start moving along in my series, I see these guys here, natural log of a half plus natural log of 2/3 plus natural log of 3/4. I don't really see a lot of cancellations going on here. But remember what natural log of a fraction is, right? It's really the difference in natural logs, right? So this is the same with properties of logs as natural log of n minus natural log of n plus 1. And that's from my log properties. And there it's a little bit easier to see that I might have some telescoping action here. When n is 1, I take natural log of 1 minus natural log of 2 plus, when n is 2, natural log of 2 minus natural log of 3. When n is 3, natural log of 3 minus natural log of 4, so on and so forth. And I see this telescoping effect, right? I see every term after the first one is going to cancel. And if I stop this series somewhere, like when n is n, right, what I'll see, my sequence of partial sums will have the first term, natural log of 1, right, my first term, minus that kind of term left over, which is going to be n plus 1. And I'm pretty much getting that right from here, right? That's just about always going to show up, and that's pretty much what we used in the last example. I just didn't make much mention of it. But really, that's going to be like our Bn, okay? Our Bn, or Bn plus 1, basically the same idea. So what we do is we take a limit there of Sn. We take a limit of that natural log piece there, and what I get is the limit as n goes to infinity of Sn, or the limit as n goes to infinity. Natural log of 1 is, of course, 0. So this is really just 0 minus natural log of n plus 1. And as n goes to infinity, this approaches minus infinity, right? As n gets bigger, natural log also gets bigger, but the negative out front makes it minus. Doesn't really matter. These terms are getting larger and larger. Okay? So this series actually does diverge. Okay? The series, this telescoping series, diverges. Okay? So a slightly different example than the one before, where we actually found a value, the limit of Sn. We actually found the limit of Bn, right, of this natural log piece, and that approached a number. Here in this example, it doesn't approach a number. So not all telescoping series converge. If they do, we can tell what they converge to. Right? So really the two series that I can say for sure that I know what the sum of the series are telescoping and geometric. Right? Let's recap just a little bit. A telescoping series looks mostly like this when I have the sum from 1 to infinity of a sub n, when these guys are going to cancel, right? If Bn converges, then the series converges, and it converges to B1 minus the limit of Bn. The series converges. So again, I look for this kind of cancellation effect. It might be a little hidden. There's some examples where they do different things, a partial fraction decomposition to show that there's actually two fractions there that are going to cancel out. So there's different examples to work through. But we're able to tell if the geometric series converges, it converges to S there. Also, geometric series. I know geometric series converges based on the common ratio of a times r to the n. I notice that each term here has an increasing power of r. This guy converges when that r in absolute value is less than 1. Then the sum is actually the first term divided by 1 minus r, and it diverges when the common ratio is bigger than, that should be, or equal to 1. Okay? So I'll try to recap these as we continue and learn different types of geometric series. There's one short extra video that I will do here with one extra test. Our first test, basically, for convergence or divergence. In fact, the next one will be of divergence for this chapter. So one more little video from 9.2. There's a kind of crash course in telescoping and geometric series. Thank you for watching.